Today we're going to start on talking about loading and the powertrain, and then in the following weeks we'll cover cornering and other instrument handling. So today we'll just look at the forces on a car. We'll talk about static loading and some of the equations you can use to come up with that. It's nothing too taxing. It's all basically level 1 dynamics, applying Newton's laws. Look at dynamic loading on the car, and then also talk about tractive force and the powertrain relationship between those things. Look at resistive models and tractive forces and those sorts of things. So those are the equations we had: low speed acceleration. So for NF and NR, okay. On one acceleration from standstill on level ground, clearly V is going to be 0. This is also only effect when it's moving. And if the ground is level, then sine of theta is 0, so that disappears. So you're left with, basically, like I said, you've got mgc, mgd, cos theta, okay? Those disappear, okay? And the aerodynamic drag disappears, and you've just got these two equations. And so, like I said, mgd, cosine of 0 is 1, so mgd and mgc you've still got, okay, and plus the acceleration or minus the acceleration. So on the front, you've got the weight of the front, which is mgd upon L, okay, mgd upon L, plus the acceleration, well, minus the acceleration, and x double dot h, okay. And obviously on the back, you've got the same thing, but you've got plus. Okay. I've got them the wrong way around on the board. Okay, right. So by dividing the equation up like this, okay, we've got the weight of the front and the weight of the rear, okay, plus or minus this term here, okay. So at the front it unloads, and in the back it loads up by the same amount. So this value, mx double dot h upon L, is known as the weight transfer, delta W, okay, due to acceleration, which is the x to the drop. Okay. Weight transfer due to acceleration is delta W. So if you know your front and rear loading in the static case, and you suddenly acceleration from low speed, you can just add on this term, okay, those values, it's in the NF and the static case, and you'll get the weight transfer due to acceleration. And clearly, you can see that's clearly dependent upon the height of the centre of gravity, your wheelbase, and the mass and the acceleration value. Okay, so have another go. The loads carried by the front and rear axles of the car when stationary on level ground is 850 and 950 kilograms respectively. Okay, it's a slightly different question. Determine the load distribution on the axles when the car is given a forward acceleration of 5 meters per second squared. If the centre of gravity is 0.54 metres above the ground level and the wheelbase is 2.8 metres, okay. What would be the load distribution if the car is given an acceleration of 5 metres per second up an incline of 1 in 12? Okay. So it's a bit more complicated. Yes?
What's the range for low acceleration?
What is the range? Well, from 0, from standstill.
From 0 to...
From standstill. Yeah.
Okay.
Because that, like I said, that gets rid of these terms. Well, not that one. These two. It's a bit more complicated when you start having V squared terms in there, and obviously the V is varying because obviously, you know, so, yeah, have a go. This, like I said, it's a bit more involved, this question, because you've got to work out C and D for yourself, okay, and L. L is straightforward. I've given it to you. The C and D you've got to work out. And the other thing I've also told you is the incline is 1 in 12, which is a different way of expressing an angle. Okay, so we'll work out what the angle is. So in class question 3, for this one we've been given the mass at the front, 850 kilograms, the mass of the rear, okay, the height of the centre of gravity is 0.54 metres, the wheelbase is 2.8 metres, and the acceleration is 5 metres per second squared. And so NF, we've got the weight on the front minus mx double dot times by the height over the wheelbase, and so that's going to be mfg minus mx double dot h over L, which is 850, 9.81 minus 1800, because mf plus mr equals m. (5 meters per second squared). 0.54 is the height divided by the wheelbase, 2.8. Six 603 newtons. For the rear load, NR, is the weight on the rear plus mx double dot h over L. So that's 950, 9.81 plus 1800, 0.54 divided by 2.8. And that comes out to be 11,055 newtons. So that's the answer to part A in a sense, okay? To work out the one with the incline, we need to work out what the angle is of the incline. Well, if you 1 in 12 is basically 1 metre up for 12 metres long. Okay, so the angle theta is going to be the inverse tangent of 1 divided by 12, which is 4.76 degrees. So NF we need to work out C and D. So let's do that. We know what MF is. That's 850 kilograms, and we know that is D upon L times by the full mass. Okay, so D equals MF L divided by M. Which is 850 divided by 1800 times by 2.8. So that comes out to be 1.322 meters. Okay. MR, the same way. MR is 950, which is Cm upon L. So C equals MR L divided by M. 950 divided by 1800 times by 2.8. Clearly the alternative way of working out what C is to take the wheelbase and subtract D from it. And it's the same thing. Okay. So just to add it together. Okay, so they're the wheelbase lengths. And so now we've got this equation, okay, but we've got the incline term in here. So the we've got the theta is now not 0. So we need to include both of those terms as well as these terms. So we can't use just that equation. That's just for low speed on low speed. Which is the acceleration from sunset. Okay. So we've got to revert back to those equations that we had up there, NF and NR. So NF, we've got MGC. Is that right? Yeah, I've got them wrong. I've just got these modeled up, haven't MG cosine of theta minus MGH sine of theta minus M x double dot H divided by L Oops.
Come on, I'd buy you a pie as well.
It's Formula One, I got research.
Everyone's trying to wait now. No. Everyone's trying to wait.
Even if it comes out like
Okay, so once you do the once you apply this equation for the case when there is an incline, so this is also when this is 0. So it's this equation we've got to use. Okay. You get 6291 as your load. Okay, so it's gone down from 6603. But the incline is now 6291 with the same acceleration. But again, for NR, I'm going to use the quick method, which is just to subtract it from there's MG minus NF. subtracted from the total normal load. So we've got 1,800, 9.81, cosine 4.76. So that's the total normal load, and we subtract 6291 from it, and we get 11,306 newtons. So we've covered these normal loads, okay, now we'll just have a look at tractive forces, okay. These are power and torque and BSFC graphs. BSFC is brake specific fuel consumption, okay, for a typical gasoline engine, gasoline meaning petrol, okay, and a typical diesel engine. Okay, so we've got spark ignition and combustion ignition, CI and SI are the other terms used, okay? And you can see that we've got slightly different shapes of graphs, okay? With a, we all know, do we know the relationship between torque and power? Power equals torque times rotational velocity, okay? And so you can see that gasoline's got quite a relatively, there's a torque curve in a sense. And so obviously power is also curved in a sense. And power will tend to, it sort of does tail off at the top end, but you end up with a peak power, quite a high RPM, okay, value. This has got an engine with about 100 kilowatts of power and about 240 or 230, about 200 degrees of torque, okay. You can see the fuel consumption, there's a peak point around here where you're going to get the minimum fuel consumption. It's specific to the power that people. That's a typical gasoline engine. With a diesel engine, okay, you can see that the torque curve is much flatter, so the power is therefore much more linear, okay. But notice that the speed that you max out at this engine is quite slow, about 2,800. But in cars, diesel engines, they run to about 4,500, 5,000, whereas the petrol engines will be sort of 6,500, 7,500. And you can see also there's a big consumption down here. So that's just an example of the different sorts of drivetrain types that can provide power. I'm going to wait until after that. So the tractive force comes from that powertrain, okay? And so if you take the tractive force and you multiply it by the wheel radius, okay, you're going to get the torque requirement at the wheels, okay? Now that has to go through a gearbox, okay? Okay, which is going to give you a ratio, which is big R, okay? And that gearbox will also have an efficiency, which is given by that symbol mu, okay? And TE is therefore the torque in the engine. Okay, so the wheel radius, torque is generated by the drivetrain, and R is the gear ratio, so the engine speed, omega E, is going to be R times the wheel speed, omega R. Okay. And that's the rotational speed of the wheel. Okay, so they're all related, so the FT, which is what we've been discussing now, okay, comes from, obviously, from the engine, and through the ratio, or the radius of the wheel, okay, and the ratio in the gearbox, you can work out the torque being required to be generated by the engine, TE. Okay. And like I said, through a certain efficiency. So FT is TE, R, N, R mu over R, okay, so if you know big R and you know little r, and the efficiency, you can work out the torque required by the engine, okay, to give you that tractive force. So the wheel power, okay, is going to be the the wheel torque times by the velocity of the wheel, okay, which is equal to the power at the engine, okay, minus the efficiency. Okay, so you've got the torque of the engine times by the speed of the engine times by the efficiency, okay, is going to give you the wheel power, okay, and that is also equal to the tractive force times by how fast you go. Okay, so they're all related to each other, all these things, okay. If you can work out the drag on a car, and if you know what power the engine's generating, okay, you can actually work out what its top speed could be from these equations, okay. Because you know, if you know the power of the engine, okay, you can work out what this is, okay. And you know the speed at which the engine's going. You can also work out what dx is, because you'll know what this term is if you know what all the drag force is. Okay. So Ft, the tractive force, is the torque of the wheels divided by the radius of the wheels, and so the power of the wheels divided by the radius and the speed of the wheels will also give you the tractive force. So everything's all related to each other. Okay, these equations all stuck together. Okay. So we know that this term equals, where is it? Torque of the wheel. This term, okay. Oh yeah, divided by R. Same equation. Yeah. And we know that this term is the power. Well, this term is the power divided by the speed. So like I said, everything's all connected to get together. So the acceleration you get out, okay, mx double dot is obviously based upon the tractive force. It's the power divided by the speed you're going around the mass. Okay. Like I said, it's all connected up. Which form of the equations you use depends on what you know. So like I said, all these different equations are all joined together. And like I said, depending on which one you want to use, it depends upon what you've been given in the question. But like I said, it's all connected together. So they're all give you the same number. So the last in-class question: petrol driven car with a mass of 1,500 kilograms has a drag coefficient of 0.3, okay, and a frontal area of 2.16 meters squared. So we've got stuff to go in the aerodynamic drag box, okay, FA. The volume resistance at the tires on the road surface is 0.01, so there's your FRL, okay. When travelling on level ground at 70 miles per hour, determine the tractive force required, okay. Assume the density of air is 1.225 kilograms per meter cubed. Note that 1 mile is 1609.34 meters, okay. So for that first part of the question, we've got enough information for the aerodynamic drag, we've got enough information for the rolling resistance, okay. And it's on a level road, so sine of 0 is 0, so that disappears, okay? We've got these two resistive forces. Work out what the tractive force is required to maintain that speed. Okay? So we're not talking about accelerating, we're just talking about tractive force required. Assume the density of air is 1.225 kilograms per meter cubed. Okay? So that's your road term. Okay? So we've got FA, FRL, work out what the tractive force is. Part 2 is go on to find out the wheel power required at 150 miles per hour. Okay? Assuming a drivetrain efficiency of 20%, the required torque generated in the engine, the gear ratio is 3 to 1 and the wheel radius is 370 meters. Okay, so let's do part A first, okay, and then when you get part A, we'll go to the solution, and then we can do part B of that question. Okay. Second class question 4, part A, okay. Basically, we want to work out the tractive force, which is the aerodynamic force, plus the resistive force due to the rolling resistance, FRL, okay. We've got the equations up there on the board. 1/2 rho CD AV squared plus CRL times by N, or R times by N. Okay. We've been given So various values. We need to work out the velocity though. That's 70 miles per hour. We know that in 1 hour you have 3,600 seconds. And we know in 1 mile we've got 1,609.344 meters in 1 mile. So the miles cancel and the hours cancel. We end up with meters per second. So this comes out to be 31.2928 meters per second, which is what we need to get force in newtons. And so, let's plug the various numbers in. Ft is 1/2. Rho, we've been told, is 1.225 kilograms per meter cubed. We've got a coefficient of drag of 0.3. We've got a frontal area of 2.16. And we've got velocity of 31.2928 squared. Plus the coefficient of rolling resistance of 0.01. And N is mg. So, because it's level ground. Okay. Do those sums, you get 535.8 newtons. There's your tractive force on level ground to maintain 70 miles per hour. Okay, let's go back to the question now. So for part B, we've got to find the power when the vehicle is travelling at 150 miles per hour. And we know the power is going to be the tractive force times by the velocity, which we'll call Vx. Now the velocity, 150 miles an hour, let's make that conversion to put it in meters per second, miles per hour. We multiply that by 1609.344 meters in a mile, and we've got 3,600 seconds in 1 hour. And if you do that sum, that comes out to be 61.056 meters per second. Now the tractive force required is going to be equal to the resistive forces that are being applied. So we've got the aerodynamic force, and we've got the force due to rolling resistance, FRR or FRL, and that's times by x double dot, which is our velocity. And so if we do this sum, we get 1/2 rho CD A V squared plus CRR times by the normal force, okay, and that's multiplied by our x double dot term. So we've got 1/2 rho, which is 1.225, CD was 0.3, A was 2.16 meters squared, and then V squared, so we have 61.056 squared, plus 0.01, which is our coefficient of resistance, and the normal force, which is mg, so 1500 times by 9.81. Okay, and that is multiplied then by 61.056. So the tractive force itself comes out to be 1,931.8 newtons times by 61.056. And so the power required comes out to be 117.95 times 10 to the 3 watts, which equals 117.95 kilowatts. Now to get the engine torque, we can use this in the equation Ft equals the torque from the engine times by the gearbox ratio times by the efficiency
divided by the wheel radius. And if we rearrange this equation for TE, we get FT times by the wheel radius divided by the gearbox ratio times by the efficiency. If we plug in the numbers, so 1931.8 times by 0.31745 divided by 3 and divided by 0.9. Doing that sum, you get 227.13 Newton meters.